Okay, section 4.2 talks about theoretical probability. It's a different way of finding calculated probabilities. In 4.1, in class, we did some empirical probability where we calculated probabilities based on data. We rolled the dice a number of times, and if we want something like, say, the probability of rolling a 3, we just rolled the dice a whole bunch of times. Collectively, we rolled the dice. Scroll down here just a little bit. There it is, 239 times. And we had the 3 come up 13 times. So the probability of us rolling a 3 based on our trials would be 13 out of 239. It's the number of successes divided by the number of trials. In theoretical probability, we think about the probability uh, based on what could happen. We think about a sample space and we look at the number of times an event occurs in the sample space divided by the number of things in your sample space. For example, if we're going to roll 2 dice, you want to think about what you could possibly get. So on die 1, you could get 1, 2, 3, 4, 5, or 6 come up. And on die number 2, your second dice, you could also get a 1, 2, 3, 4, 5, or 6. And so if we think about what could happen, if I get a 1 on the first dice and a 1 on the second dice, then the sum would be 2. If I get a 1 on the 2 on the first dice and a 1 on the second dice, the result would be a 3. 3 and 1, the result is 4. 4 and a 1, the result is 5. 5 and 1, the result is 6. And a 6 and a 1, and the result is 7. Or maybe I could get a 2 on the second dice and a 1 on the first dice, and then the sum would be 3. 2 on both dice gives us a sum of 4. A 2 on the second dice and a 3 on the first dice gives us a sum of 5. 5 there. 4 and a 2 is 6. 5 and a 2 is 7. 6 and a 2 is 8. And so we could go on and kind of fill in this whole table about all the possible sums that we could come up with. Let me do it here kind of really quick. Uh, I need a little bit more space. Scroll down here a little bit for me. Uh, there we are. No, don't slide over. Scroll down. Okay. 7, 8, 9, 10, 11, and then 12, which is when you get that 6 in the 6. And so if you look at the probability of getting a 3, that 3 is happening in our table twice. And then if you count the total number of things, it's a 6 by 6 grid. There are 36 possibilities that are coming out there. So the theoretical probability of us rolling a 3 is 2 out of 36, whereas the based on our trials, we had it happen 13 out of 239 times up there. So your theoretical probability is you list all the outcomes. That's your sample space, is your list of all the possible outcomes. And then when you're looking at your probability, whatever event that you're looking at, you want to look at how many times it happens within your sample space there. How about another example? If you're flipping a coin twice and you want to list the sample space, you want to think of that, well, you could get a heads on the first dice, on the first coin, and a heads on the second one, a heads and then a tails, or maybe you'll get a tails then a heads, or you could get 2 tails. So there are 4 possible outcomes there in our sample space, and we like those to be equally likely, and I would assume those are equally likely. And so the probability of you getting 2 heads would be 1 out of 4. That's happening once out of the 4 options in there. So you want to list out your sample space. Sample space is the list of all your possible outcomes. All right. We did that thing on Friday, pulling from the bag, where we pulled out those tiles out of the out of the bag. And if we look at if what's in there, you may have looked in there, or you may not have looked in there. But if you look at the probability of getting the red tile, there is one in there. I know some of you might doubt that, but there is one in there. And if we count the number of tiles, there's a total of 20 tiles. So your theoretical probability of getting that red tile is a 1 in 20 chance. Or if you like it as a decimal, it's 0.05 or it's 5%. You got a 5% chance of getting that red tile coming up. It didn't happen very often for the most part, but it was a probability in there. Okay, some other questions that we can do is maybe, well, looking at this in your bag, you had different colors. There's some yellow ones, some green ones, some blue ones, sort of thing. And those varied a little bit, but there was a total of 20 tiles, and one of those 20 tiles was red. But if I looked at, say, if this was the bag that we were looking at, what would the probability that we end up with something blue? And we're still looking at 20 tiles in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of them are blue. So the probability of getting a blue tile would be, yeah, 11 of them would be 11 out of 20 would be the probability of getting a blue tile in there. Uh, so you just want to think about that sample space. What are all the possible options, and then how often does the thing that you come up with occur? There are a couple of nice um, probability rules out there. That are kind of helpful. We can sometimes talk about the complement event, which would be like the probability of not getting blue. So that would be you look at the probability that you don't come up with blue. Let me look at that. Uh, let's make that a little bigger so you can see it here. There we are. Probability rules. The probability that you don't get blue is 1 minus the probability of blue. So that BL UE. Let's spell blue correctly there. So the complementary of the event is 1 minus the probability. So the probability that I don't get blue would be, um, back to my pen here, that would be 1 minus 11 out of 20, or it would be 9 out of 20. That the probability that I don't get a blue one is 9 out of 20 in there. So probability of a complementary event. So if you look at, if you're looking at the success of A, the probability that A doesn't happen is 1 minus the probability of A. If you're doing, there's the addition rule. Uh, addition rule. And that is the probability of A or B. Gonna make my default font size larger. That if you're looking at sort of two options, if you're looking at multiple ways of winning, typically we'll look at two different options there. Probability of A or B is the probability of A uh, plus the probability of B, assuming A and B are mutually exclusives. That means that they don't happen. EXCLUSIV. Mutually exclusive, that they can't both happen at the same time. So we're not looking at, I don't have any tiles that are, partly red and partly blue. So when I get a blue one, it counts as both a red and one of these partially covered counts as both blue and red at the same time. So a lot of times when you're looking at something like that, you're going to add those two. and that's a useful thing to do there is to that addition rule. And then there's also the multiplication rule. Uh, a lot of times when you're looking at two random events, so in the addition rule, you're typically looking at one random event, but you've got two different outcomes as a success, and we can add the probabilities of each value independently. In the multiplication rule, you're multiplying two things together. You have two random events, and you can multiply the probability of the two things together. So if I'm looking at, say, uh, if I am going to, well, what if I draw uh, two things from the bag, two tiles? Let me go to, let me type it because that looks prettier. Start off with it big. Uh, we'll draw two tiles from the bags. And I want to know what's the probability that both are blue. What's the probability that both are blue? Well, if we go back and look, and there's kind of two ways to do that. There's with replacement. So in with replacement, you do it. You put the first tile back in the bag uh, after you do it. So the probability of blue and then a blue. If I remember correctly, it was 11 out of the 20 based on the sample that we were using above. So it would be 11 out of 20 times with replacement, it's also going to be 11 out of 20. So it's going to be, oh, wow, it calculated that for me. That's pretty cool. It should be like 121 divided by 400, which apparently is 30.025. I didn't know that it would do that. That is pretty cool. That this one note that I'm using did that for you. So you got about a 30% chance of getting two blue tiles in a row. And then you could also look at without replacement, where we keep the first tile out uh, before we draw the second. And it's very similar. I still want to multiply. I want to take 11 out of 20 as the first one, but the second one, there are only 10 blue tiles left in the 10 blue tiles out of the 19 that are left in the thing, in the bag. So it would be 11 20ths times 10 19ths for the value there. And it would be a slightly smaller percentage, right? A little bit less likely to get the blue tile on that second draw because there are fewer blue tiles in the bag. So when you're doing this multiplication rule, when you're looking at sort of two random events in there, you want to multiply the two values together. So your 4.2 homework has you thinking about sample spaces and calculating probabilities from those sample spaces as well. All right. If you have any questions, we do have there should be a discussion forum in the homework, so or in Canvas, so you can ask those questions, and we will see what we can do there to answer those. But the theoretical probability, again, is you're thinking about what are all the possible outcomes. You want to generate that sample space what's the list of the possible things you can come up with, and then you look at what successes do you have within that sample space, out of how many total values there are. All right.